Tonight, we're going to the end of everything. Not the end of a mission, not the edge of the solar system, the end of the universe itself. Imagine this. You open your eyes in a future so distant that every star has gone out. No sunrise, no planets glowing in reflected light, no familiar night sky. Just a thin, cold haze of radiation. And somehow, against all expectation, you are still there. Your body no longer looks like it does today. There is no warm blood, no busy brain, no rushing biological wind of signals and cells. On human timescales, everything about you seems fragile and temporary. A century feels long, 1,000 years feels unimaginable. But the universe does not think in centuries, it thinks in powers of 10 trillion years, 10 undecillion years, a 1 followed by 100 zeros. Some cosmologists think the universe has already decided how all of that ends, not in a mystical way, but in the cold language of physics. The same equations that describe the expansion of space and the fading of starlight also reach forward to the fate of your atoms, your memories, even your information. In that view, the ending is written into the mission profile of reality. The universe is just waiting to catch up. Before we get started, place yourself on that timeline. Right now, you are a brief pattern of energy and matter inside a young, bright cosmos, only 13.8 billion years into its run. In a mere 10 to the 14th power years, star formation stops. The last new suns flicker into existence and then go dark. In about 10 to the power of 34 years, if protons decay, every familiar atom in every planet and spacecraft quietly dissolves into radiation. By 10 to the power of 100 years, even the largest black holes evaporate, releasing the final whisper of the universe's hidden history. Tonight, we're going to walk that entire arc, step by step, from your living neurons today to the last possible trace of information they could leave behind. This is not just a journey across space, from galaxies to the void beyond their boundaries. It is a journey across all of time, from a universe filled with stars and planets to its final, silent seconds, and what those seconds mean for you personally. Along the way, there are multiple ways everything can end. A vacuum decay bubble could appear without warning, racing outward at nearly the speed of light, rewriting the laws of physics and annihilating every structure instantly. Dark energy could tear galaxies, solar systems, and finally atoms apart in a catastrophic big rip. Or expansion could continue forever, slowly stretching all energy into a thin, uniform fog in a heat death so quiet that no one expects a final moment at all. By the end of tonight, you're going to understand which of these endings current physics treats as wild speculation, which remain on the table, and which the best measurements quietly favor. Now, let's begin. To understand how the universe kills you, you first have to understand that it has options. Heat death is the quiet assassin. Expansion continues, energy spreads out, and space thins into a uniform, lukewarm fog where no new structure can ever form. The big rip is the violent one. Dark energy grows with time until it tears apart galaxy clusters, galaxies, solar systems, planets, and finally atoms themselves. The big crunch is the reversal. Expansion halts, then runs backward, dragging all matter and radiation into a final, crushing fireball. And vacuum decay is the trapdoor. A bubble of lower energy vacuum appears out of quantum nothing, races outward at nearly light speed, and rewrites the laws of physics as it passes. Each of these endings does something different to you, not just to your body, to your atoms, to the information that once described every memory you have, every neuron that ever fired, every heartbeat you ever felt. In one universe, you fade into a thin rain of photons over 10 to the power of 100 years. In another, you are ripped apart long before the last star goes dark. In a third, you are squeezed into a final furnace that makes the Big Bang look gentle. In the fourth, you do not even get a last second to look around. Tonight, we're going to treat these not as distant theories about galaxies, but as personal endings. If the mission of cosmology is to understand space and time, then the side mission is unavoidable. Understand what happens to you when space and time themselves run out. Before we get started, remember how wrong early models of the solar system's edge were. Scientists pictured a neat, spherical boundary where the solar wind simply stopped. Then spacecraft ventured beyond the planets and discovered a messy, stretched, asymmetric heliosphere that no one predicts from the first sketches. The same thing has happened with the universe. The earliest ideas about a simple recollapse or a gentle coast into darkness were elegant but incomplete. Modern measurements of dark energy, of the cosmic microwave background, and of the way galaxies move have radically updated the picture. The universe is not just expanding, that expansion is accelerating. That one fact reshapes the menu of endings, pushes the Big Crunch into the background, elevates heat death and the Big Rip, and leaves vacuum decay lurking as a quantum wildcard. So here is the promise. In this video, the universe's death will not be a single moment. It will be at least 7 distinct stages. From the age of stars to the age of black holes, from the decay of matter to the fading of the last radiation, you will be able to trace a continuous story from your life right now to the last flicker of physics itself. By the end of tonight, you're going to understand not just how the universe ends, but where, on that unimaginable timeline, you finally vanish, and whether anything of you can cross the final boundary. But to see that, we have to start the clock on the first stage, where the universe still looks familiar. For now. So why should any of this matter to you when the numbers involved make the age of your entire civilization look like a rounding error? You have bills next week, deadlines tomorrow, messages waiting right now. 10 to the power of 100 years feels like another universe. That objection is reasonable. It's the default setting. No one expects a video about the universe's death to be secretly about you. But the moment the question shifts from when do the last stars go out to what does that do to the meaning of your one short life, the timeline stops being a trivia fact and starts becoming a mirror. Because this isn't just a story about atoms cooling in empty space. It's a story about what happens to what you are. Not your height or your job or the particular atoms in your hand right now. Those atoms are already being swapped out all the time. What persists is the pattern, memories, habits, the way your nervous system responds to a friend's voice, the trail of photos, messages, and records you leave across the planet. In physics language, that pattern is information. You are a configuration written into matter and energy. The way a song is written into vibrations in air or bits on a hard drive. Destroy the medium and the pattern can vanish. Copy the pattern onto a different medium and the song survives, even if every original atom is gone. Tonight, we're going to push that idea out of the room, out of the solar system, and into the far future. Because the universe's death is not just about the last star flickering out. It is about whether information itself can ever truly be erased. Quantum theory has a brutal opinion on this. The equations say information must be conserved. Black holes can evaporate over around 10 to the power of 100 years, but their Hawking radiation might encode, in an unimaginably scrambled way, everything they ever swallowed: stars, planets, and every trace of you that fell in. If that's true, then in principle, some ghostly, encrypted shadow of your pattern could outlast galaxies, outlast the solar wind, even outlast the black holes that end the mission of ordinary matter. No one predicts that this you is conscious or recognizable. But absolutely no one anticipates how strange it feels to realize that physics may refuse to forget you completely. Now, let's begin to connect this to your choices. Suppose every memory, every action is written into the universe in a way that cannot be fully deleted, only transformed and dispersed. Does that make your life more meaningful? Because nothing is ever truly thrown away. Or does it feel more fragile because even if some trace survives, the warm first-person experience does not? By the end of tonight, you're going to understand how different cosmic endings, heat death, a big rip, even a sudden vacuum decay, treat information, and what that means for any version of you, biological, digital, or purely informational. In the next section, the timeline will start to accelerate, and the question will sharpen. Not just how long the universe lasts, but whether any form of you can ride it all the way to the final boundary. To understand your ending, you need to know what you were born into. Right now, you live in a universe that feels timeless and stable. It is neither. It is a young racing experiment in expansion and decay. Current measurements say the universe is about 13.8 billion years old. That sounds ancient. Civilizations rise and fall in thousands of years, planets and stars in billions. But on the timescales that will decide your ultimate fate, 10 to the power of 34, 10 to the power of 100 years and beyond, 13.8 billion is the first second after midnight. A brief flash at the very start of the cosmic recording. Before we get started on how it all ends, lock in what exists right now. The space around you is filled with three main ingredients. First, normal matter, the atoms that make your body, the planets, the stars, the gas, and dust between them. Second, dark matter, invisible mass that reveals itself only through gravity, binding galaxies together and sculpting the large-scale structure of the cosmos. And third, the strangest component, dark energy. Dark energy does not behave like matter. It does not clump. It does not form planets or spacecraft or solar systems. It appears as a smooth energy density built into space itself, and it is driving the expansion of the universe to accelerate. Galaxies are not just drifting apart. The rate at which they recede is increasing, as if some hidden pressure is pushing on the very fabric of the cosmos. Tonight, we're going to treat dark energy as the main suspect in your final disappearance. Because the universe is not static, its expansion rate and its energy content work together like a cosmic mission profile. Change the mix, and you change the ending. A little more matter and a little less dark energy, and the universe might have slowed, stopped, and collapsed in a big crunch. A different, more violent form of dark energy, and distant galaxies might not just drift away, but be torn from each other in a catastrophic big rip. To feel how early you really are, compress the entire life of the universe so far into a single calendar year. The Big Bang is at midnight on January 1st. The Milky Way's basic structure emerges by spring. The solar system forms in early September. Dinosaurs roam in late December, then vanish. Modern humans appear at 11:52 p.m. Your entire lifetime, a fraction of a second before midnight, a thin line of awareness on a page that has barely been written. By the end of tonight, you're going to understand that this calendar does not stop at December 31st. It stretches far beyond into years whose numbers are written as powers of 10. To see how the universe dies, you first need a quick tour of how it lives and evolves, how expansion stretches space, how entropy grinds order into randomness, and how those two trends working together slowly erase every boundary that could ever separate you from the dark. To see that story, you have to learn the rules of the game, not human rules, cosmic rules. Tonight, we're going to walk through the three that decide how everything ends: expansion, entropy, and dark energy. First, expansion. The universe is not a bomb going off into empty space. Space itself is stretching. Galaxies are not flying through a pre-existing void like shrapnel from an explosion. Instead, the void between them is growing. Imagine tiny ink dots on the surface of an inflating balloon. None of the dots move across the rubber, yet the distance between every pair increases as the balloon expands. On cosmic scales, you are one of those dots. This stretching was discovered when scientists noticed that light from distant galaxies is redshifted, its wavelengths elongated, like sound from a receding siren. The farther a galaxy is, the faster it appears to recede. That relation is not about rockets firing. It is about the metric of space changing frame by frame as the whole system evolves. But expansion alone does not tell you how your universe feels from the inside. For that, you need entropy. By the end of tonight, you're going to understand why the future is always messier than the past. Entropy is a count of how many microscopic arrangements correspond to what you see macroscopically. A neat room has relatively few ways for every dust grain, book, and photon to be arranged. A wrecked room has vastly more. The wrecked state wins, not because nature prefers chaos, but because there are more ways to be disordered than ordered. The same logic scales to galaxies and planets and to your own body. Low entropy configurations, cold gas clouds collapsing into stars, chemical gradients powering cells, are rare, precarious islands in a sea of higher entropy. Left to itself, any closed system drifts toward the most probable macrostate, the one with the most microstates. That slow drift is what you experience as time's arrow. Here is the pattern interrupt. The early universe, hot, dense, and apparently uniform, looks high entropy. It is not. Gravitationally, it is astonishingly ordered. There were almost no clumps, no black holes, no galaxies. That smoothness was a low-entropy starting gun, a charged battery. It allowed gravity to gradually sculpt structure. First stars, then planets, then the solar system, then a planet where a brain could ask how all this ends. That battery has been discharging for 13.8 billion years. Enter dark energy. In the late 1990s, distant supernovae revealed that cosmic expansion is not merely continuing, it is accelerating. Some invisible component of the cosmos behaves like an energy of empty space itself, nearly constant everywhere, pushing galaxies apart faster and faster. No one expects a vacuum to have weight. No one predicts that weight will drive the ultimate fate of all planets and black holes. And absolutely no one anticipates how strange the consequences become when this repulsion dominates everything. If dark energy remains constant, expansion keeps accelerating until galaxies drift beyond each other's horizons, and entropy grinds toward a thin, cold heat death. If dark energy grows stronger with time, it can rip apart galaxies, then solar systems, then atoms in a final big rip. If it changes sign or decays into something new, the endgame could be a catastrophic collapse or a sudden rewrite of the vacuum itself. Now, let's begin to follow you into those endings. By doing something almost no one expects. Putting your tiny human lifetime on the same timeline as the universe itself. An average human gets, with luck, about 80 years, 8 decades, around 2.5 billion seconds. That sounds huge from the inside. You feel the drag of a workday, the stretch of a bad year, the weight of a lifetime. But on the scale of cosmic time, 80 years is not just small, it is indistinguishable from zero. Before we get started on the far future, anchor that 80-year span. Picture a timeline on your wall. Birth at the left, old age at the right. Now zoom out until that entire line shrinks to a single pencil mark. That's your life compared to recorded human history. Zoom out again until all of civilization, 10,000 years of cities and writing and missions into space, collapses into a thin hairline. That's human history compared to the age of the solar system. Now keep going. The solar system is about 4.5 billion years old in a universe that's 13.8 billion years old. On this scale, the rise and fall of entire continents, the evolution of life, the extinction of the dinosaurs, and every spacecraft ever launched are all flickers in a single frame. By the end of tonight, you're going to understand why even this entire history is just the opening credits. Tonight, we're going to push beyond billions. In roughly 10 trillion years, around 10 to the power of 13 years, the last normal stars burn out. By about 10 to the 14th power years, new star formation ends. Compare that to an 80-year life. You would need to live and die 100 trillion times just to personally witness that era arrive. Then the numbers stop feeling like time at all. If protons decay, a single proton might last around 10 to the 34th power years. That is 20 orders of magnitude beyond the death of star formation. Take the already incomprehensible gap between your life and the end of stars, then multiply that gap by 100 billion, and you are only now approaching proton decay. Farther still, black holes evaporate through Hawking radiation on timescales approaching 10 to the power of 100 years. The difference between 10 to the power of 34 and 10 to the power of 100 is far larger than the difference between 1 second and the entire current age of the universe. At this point, ordinary intuition fails. Clocks still tick, but the mind has no reference. And yet scientists can write down equations, run simulations, and make concrete predictions about how space expands, how matter falls into black holes, how radiation spreads, and how information seeps back out. No one predicts the exact details of every collision, but the large-scale story of energy, entropy, and decay follows rules that can be traced far beyond any star, any planet, any solar system. The real question is, where are you on this timeline? In the next section, the mission changes. That pencil mark that was your life will stretch again, and your body, your atoms, and your information will be marched, step by step, into futures so long that absolutely no one anticipates what they feel like from the inside. From here, the mission enters its longest phase. Tonight, we're going to ride the timeline from your brief human moment into the slow, glowing middle age of the cosmos, the stelliferous era, the age of light. Now, let's begin. The universe is about 13.8 billion years old. Stars have been shining for most of that time, and new ones are still switching on. Galaxies are busy construction sites. Gas clouds collapse. Stars ignite. Planets assemble. By the end of tonight, you're going to understand where that activity fits on the full timeline and how long anything resembling the current universe can survive. Scientists call this span the stelliferous era, the era in which stars dominate the energy budget of space, from roughly a few million years after the Big Bang to around 10 to the 14th years in the future. The main visible actors are stars, galaxies, and the structures you already recognize. You are living almost exactly in the middle of this bright window. To you, it feels permanent. To the universe, it is a transient flare. Here is the expectation: stars keep forming as long as there is gas. The reality is harsher. Every generation of stars locks more hydrogen into dead remnants or blows it out of galaxies entirely with fierce radiation and stellar wind. Over trillions of years, the raw fuel is slowly sequestered in white dwarfs, neutron stars, and black holes. Star formation rates fall, then fade, then almost vanish. Projections suggest that by around 10 to the 14th years, new stars effectively stop forming. Not because some cosmic switch flips, but because nearly all the easy gas is gone or gravitationally trapped. The great factories shut down, one by one, until the universe is left to live off its remaining inventory. Those remaining stars follow very different paths. Massive blue stars burn through their fuel in only millions of years, then explode as supernovae, leaving behind neutron stars and black holes. Medium stars like the Sun glow for billions of years, shed their outer layers, and cool into white dwarfs. Tiny red dwarfs, the most common stars in the galaxy, sip their fuel so slowly that some will shine for 10 trillion years or more. No one predicts their full life cycle from direct observation, because not a single red dwarf has had time to die yet. What does this mean for you? The atoms in your body are already recycled starlight, carbon from ancient supernovae, calcium from long-dead suns. In the stelliferous era, those atoms will be used again and again. A carbon atom in your bone might spend the next trillion years locked in a red dwarf, then blown into space, then folded into a new planet, then into another creature that looks up and wonders what the universe is doing. Through all this, the broad scene remains familiar. There is still a night sky with stars. There are still galaxies, spiral and elliptical, still clusters and filaments tracing the large-scale structure of the cosmos. The solar system is long gone, but the environment would not feel alien in the way later eras will. Light still defines what is near, what is far, what is home. But even this age has an ending. As the last reserves of gas are used, as red dwarfs finally exhaust their cores, the number of shining stars dwindles. Imagine a universe where most galaxies are dark husks, punctuated by few lingering embers. Somewhere, in that vast, mostly empty space, one final red star burns alone. No one expects that last star to be special. It is just the slowest fuse. When its fuel finally runs out, the universe crosses a boundary that has never been crossed before. For the first time since the cosmic dawn, there are no new stars, no old stars, no stars at all. Imagine being conscious then. Imagine existing in a cosmos where the last point of light goes out and the sky that was once crowded with suns becomes an endless, perfect dark. What does it feel like to watch the universe forget how to shine? This is where the universe goes from dim to truly dark. The moment the last star dies, a new age begins with almost no light, no warmth, and no second chances. Scientists call this the Degenerate Era. It's the time after the cosmic fireworks are over, when the universe is filled not with blazing suns, but with their corpses. White dwarfs, neutron stars, black holes, and cold, wandering planets. Tonight, we're going to walk through this graveyard and see what it does to everything you have ever been. White dwarfs, the exposed cores of dead stars, keep shining for a while, but without nuclear fusion they only glow by slowly leaking the heat trapped inside them. Over trillions, then quadrillions of years, they cool from white to red, from red to infrared, and finally to black, becoming invisible black dwarfs that no one predicts will ever be seen by a living eye. The universe keeps expanding. The background temperature keeps falling. The embers fade. Neutron stars, once spinning dozens or hundreds of times per second, gradually lose energy too. Their magnetic beacons slow and dim. Their radio pulses switch off, and they become silent, city-sized spheres of ultra-dense matter drifting through space. Planets do not fare much better. As stars lose mass and gravitational balances shift, many planets are gravitationally ejected from their systems, flung into interstellar space as rogue worlds, frozen, airless, and alone. The quiet is not absolute. Over absurdly long timescales, orbits decay. White dwarfs in tight binaries spiral together and merge, sometimes igniting a final supernova. Neutron stars collide, forging heavy elements and releasing brief, violent flashes of gamma rays. Black holes swallow unlucky stars, planets, or each other, lighting up their surroundings for a moment before the dark closes in again. But compared to the blazing past, these are rare, isolated sparks in an almost perfect night. By the end of tonight, you're going to understand that by this stage, the atoms that once made you are unrecognizable. No one expects a coherent body, a brain, or a memory to survive this long. Those atoms are now fused into the crystal lattice of a black dwarf, dissolved into thin interstellar gas, or locked inside a frozen planet drifting beyond any familiar boundary. There is no record of your thoughts, no archive of your experiences, except as patterns of energy long since thermalized into the background. And yet, imagine something enduring, a civilization, or a chain of consciousness that somehow threads its way into this era. Before we get started on the ultimate end, consider the question that absolutely no one anticipates needing to answer. In a universe where usable energy is running out, where every mission is a fight against entropy, what strategies could anything intelligent use to keep going? Now, let's begin to explore just how desperate and how strange that struggle might become. That desperate, strange struggle only matters as long as there is something to struggle with. At some point, the universe may attack the problem at its root, not by dimming stars, not by freezing planets, but by quietly unmaking matter itself. Tonight, we're going to step into a timescale that makes even dead stars feel young. Grand, unified theories predict that protons, the positively charged particles in every atomic nucleus, are not truly eternal. They might decay incredibly rarely with lifetimes of around 10 to the 34th years or longer. For comparison, the universe today is just 1.38 times 10 to the 10th years old. On this scale, everything you know is a brief electrical flicker. The idea is simple to state and hard to accept. If protons decay, then every atom in the solar system is living on borrowed time. Hydrogen in interstellar space, carbon in planets, oxygen in white dwarfs, the heavy elements forged in supernovae, each proton in each nucleus is a ticking quantum clock. The mission of decay is patient, but it never stops. By the end of tonight, you're going to understand how that patience reshapes the far future. Imagine the universe long after star formation has ended, after red dwarfs and white dwarfs have cooled into black, lightless remnants. Those remnants seem permanent. They look like the final, frozen architecture of matter, but if proton decay is real, that impression is wrong. The boundary between solid object and empty space starts to blur. Over 10 to the 34th, 10 to the 40th, 10 to the 100th years, protons inside those dead planets and stellar corpses randomly transform into lighter particles, positrons, neutrinos, and showers of radiation. A white dwarf doesn't crack or explode. It evaporates from the inside out, dissolving into a thin mist of subatomic particles drifting through expanding space. Planets do the same. The last mountains never erode. They simply stop being made of matter. Pattern interrupt. This is not guaranteed. No one predicts proton decay as a certainty. Scientists have built enormous underground detectors, watching vast tanks of ultra-pure water for the telltale flash of a single proton giving up. Decades of observation have discovered nothing, only pushing the lower limit on the proton's lifetime, higher and higher. If decay never happens, the universe's endgame looks different. If it does, the long-term fate of every structure changes dramatically. Now, let's begin to connect this directly to you. At this stage, your body is long gone, your planet, your star, your galaxy's bright disk, all gone. But proton decay goes further. It erases the very identity of the particles that once composed you. The protons that held your atoms together don't just move or cool. They transform into entirely different particles, lost in an almost perfect darkness. What remains is not a ruined version of you, not even scattered atoms with a shared history, but a diffuse radiation field and a sprinkling of light particles with no memory of their origin. In a universe ruled by proton decay, physical continuity is severed. To trace you across time, future physics would need more than matter. It would need a way to preserve information when even the building blocks have forgotten they were ever part of a person. When matter forgets it was ever part of you, something else steps in as the universe's memory. Tonight, we're going to follow the rise of the last giants, black holes. As stars fade, as planets erode, as the familiar architecture of the solar system dissolves, black holes remain. They are born from the deaths of massive stars and from the crowded hearts of galaxies, where millions of suns once orbited a single invisible anchor. When fusion has ended everywhere and proton decay has thinned normal matter into a ghostly radiation field, these collapsed remnants become the main long-lived structures in space. No one expects how quiet their empire is, no glowing disks, no bright jets. Just dark spheres drifting through an almost perfectly empty universe. A stellar mass black hole, maybe 10 times the mass of the Sun, circles alone for unimaginable spans of time. Supermassive black holes weighing as much as billions of suns sit where galactic centers used to be, now ruling over nothing. But even these giants are not eternal. At the edge of each black hole there is a boundary, the event horizon. Cross it, and no signal, no spacecraft, no light can ever return. Classical physics says that's the end of the story. Quantum physics quietly disagrees. Near the horizon, the vacuum is not empty, It seethes with pairs of virtual particles that flicker into existence and then annihilate. Usually both partners fall back together and disappear, but if this happens right on the horizon, one partner can fall in while the other escapes. To a distant observer, that escaping particle looks like radiation leaking from the black hole. The hole loses a tiny bit of mass to pay the energy bill. This slow glow is Hawking radiation. Now let's begin to feel the time scales. A black hole the mass of the Sun would take about 10 to the power of 64 years to evaporate. Not million, not billion, a 1 followed by 64 zeros. The largest supermassive black holes that scientists have discovered in the centers of giant galaxies could last around 10 to the power of 100 years before they finally vanish. By comparison, the current age of the universe is only 1.38 times 10 to the 10th power years. The entire era of stars is a brief prelude. By the end of tonight, you're going to understand just how empty the black hole era really is. Picture a universe where almost everything is gone. No bright planets, no galaxies, just isolated black holes scattered across a volume so vast that many will never encounter even a single stray particle before they die. Between them, a thin bath of low-energy radiation, the faded afterglow of all previous ages. In this darkness, black holes are more than objects. They are vaults. Each one holds, in some encoded way, the information of everything it ever swallowed. Stars, worlds, spacecraft, entire civilizations, perhaps even particles that once passed through your body. When the last giants finally evaporate into a whisper of Hawking radiation, what happens to that information? Does the universe's final memory of you dissolve with them, or does something deeper survive beyond the last horizon? If black holes are the universe's final memory banks, then what happens when even the memory banks burn down? Tonight, we're going to follow them all the way to their last flicker. As a black hole evaporates through Hawking radiation, it does something deeply unintuitive. Losing mass makes it hotter. Smaller means angrier. The radiation grows more energetic, not less, and the rate of evaporation accelerates. A supermassive black hole weighing millions of suns might take around 10 to the 100th years to reach this late stage, quietly leaking particles into space for incomprehensible ages before the process suddenly runs away in its final instant. Near the end, the contrast between expectation and reality becomes extreme. You might imagine a black hole fading out like a dying ember, slowly dimming into nothing. Instead, theory predicts a brief, violent finale. A burst of high-energy photons and particles, a last flash of concentrated power in a universe that has forgotten what brightness looks like. For a fraction of a second, that region of space is more energetic than entire galaxies are today. Then the horizon vanishes. The well is gone. By the end of tonight, you're going to understand why that disappearance matters more than the flash itself. While black holes exist, they carve deep, gravitational boundaries into the cosmic landscape. They trap matter, curve time, and provide gradients in energy that, in principle, could still be harvested by hypothetical civilizations or exotic spacecraft far beyond anything scientists can currently build. They are engines waiting to be tapped. When the last black hole evaporates, those engines shut down forever. No one predicts a new generation of structures to replace them. No one expects fresh stars to ignite or new planets to form. With no more gravitational wells that can significantly trap or process energy, the universe loses its final organizers, the last places where complexity can be amplified instead of erased. What remains is almost offensively simple, an ever-expanding space filled with a thin, cold bath of radiation and a few relic particles. Photons stretch to absurd wavelengths by cosmic expansion, carrying energies so low they would be impossible to detect with any realistic instrument. Neutrinos drifting through volumes larger than today's visible universe without hitting anything. Perhaps the lightest stable particles, electrons, or something even more subtle if proton decay has long since dissolved ordinary matter, diluted to less than 1 per unimaginable cubic light-year. This is heat death in action, not as a slogan but as a physical state. Maximum entropy. No free energy gradients left to drive wind, chemistry, stars, life, or computation. Every region of space looks, on average, like every other region. The cosmic game board is still there, but there are no legal moves left. Now, let's begin to ask a harder question. In a universe where nothing interesting can happen, does the concept of you, or any observer, still have physical meaning? If no structure can form, no memory can be written, and no mission can launch, can there even be an experience of that final darkness? Or is there one last twist waiting beyond this quiet, frozen horizon? In the heat-death future, that question has a brutal answer. The universe does not just become quiet, it becomes perfectly, irreversibly still. Tonight, we're going to walk into that stillness and see what it really means for you. Heat death sounds dramatic, but in physics, it has a very precise meaning. It is the state where the universe has reached thermodynamic equilibrium, where energy is spread out so evenly that no macroscopic process can occur. No engines can run, no chemical reactions can sustain themselves, no mission can ever launch. By the end of tonight, you're going to understand why that also means no mind can think. There is a common misunderstanding. Heat death does not mean the universe ends in a blazing inferno. It means the opposite. Temperature is not about how hot something feels, but about how energy is distributed. When every region of space has the same temperature, there is no gradient, no higher and lower, no way to extract useful work. In the far future, that common temperature drifts toward an incredibly cold, near absolute zero value, almost the same everywhere. Right now, stars burn because there is contrast, hot cores, cooler space, flows of energy. Galaxies form because gravity can pull matter into dense knots surrounded by emptier regions. In a heat-death universe, that contrast is gone. The cosmic background has faded, stars have died, black holes have evaporated, and the last stray photons and particles are smeared across an ever-expanding volume. The boundary between here and there loses all practical meaning. Could something still spontaneously appear? Quantum mechanics allows fluctuations, tiny, random deviations from perfect uniformity. But the statistics are merciless. Small fluctuations are common, large ones are fantastically rare, and organized structures are essentially impossible. A single particle might momentarily gain energy. A galaxy-sized structure, or a functioning brain, is so unlikely that even across 10 to the power of 100 years and beyond, the probability is effectively zero. No one predicts a late-time comeback for complex life. Here is the strange twist. In principle, the micro-state of this final thin mist of radiation and particles still encodes everything that ever happened. Every collision, every star, every planet, every thought. Information in quantum theory is hard to destroy. But in practice, it is scrambled beyond recognition, spread across an astronomical number of degrees of freedom. inaccessible to any observer because there are no observers left. So, what does that mean for you? Before we get started on exotic loopholes, face the direct implication. Any physical, biological, or digital trace of you has long since vanished. Your atoms have been unbound, your memories erased, your data overwritten by eons of thermal noise. What remains is only a statistical contribution to the universe's total entropy, an immeasurably tiny influence on how perfectly mixed the final radiation sea has become. Pattern interrupt. Imagine trying to rewind that sea to recover a single human life. The equations say the information is there. The reality is that no spacecraft, no scientists, no system of planets or machines exists to read it. Now, let's begin to ask an even more unsettling question. If information can never truly be destroyed, is there any meaningful sense in which you survive this perfect graveyard? Or does survival require more than just being hidden in the noise? If the heat death is a slow fading into silence, there is another option that feels more like a cosmic scream. Instead of the universe freezing into a thin, quiet fog, space itself could decide to pull everything apart. Not gradually, violently. Before we get started, remember what is driving the expansion right now. Dark energy. In the standard picture, its density stays roughly constant as the universe grows, stretching the distance between galaxies but leaving smaller, gravitationally bound systems intact. But there is a more extreme possibility. If dark energy's density increases with time, a form sometimes called phantom energy, then the expansion does not just continue, it accelerates without bound. Tonight, we're going to follow that acceleration all the way to its logical conclusion, the Big Rip. In this scenario, the equations say there is a finite time in the future when the scale factor of the universe blows up to infinity. The distance between any 2 points in space grows so fast that no force, no bond, no structure can keep up. By the end of tonight, you're going to understand what that means for galaxy clusters, for planets, and for you. The sequence of destruction has a grim, ordered beauty. Long before the final moment, billions of years out, the largest structures go first. Galaxy clusters that once held hundreds or thousands of galaxies together lose the tug-of-war with runaway expansion. The space between them grows faster than their combined gravity can pull back. The cosmic web unthreads. Closer to the end, individual galaxies are attacked. Stars that have orbited peacefully for tens of billions of years are flung away as the expansion overwhelms the galaxy's own gravity. What used to be a coherent spiral or elliptical system dissolves into a spray of isolated stars, each marooned in rapidly stretching space. As the clock ticks down to mere millions of years before the rip, solar systems lose their grip. The pull between a star and its planets is no longer enough. Orbits elongate, then fail. Planets are peeled away and hurled into the accelerating darkness. In the final minutes, even planets cannot hold themselves together. The force driving expansion across their diameters exceeds the chemical and gravitational bonds in their interiors. Crust, mantle, and core are torn into fragments. Then the scale changes again. In the last fractions of a second, atoms themselves are pulled apart. Electrons are ripped from nuclei, then the nuclei are shredded into protons and neutrons, and those in turn are forced apart into their constituent quarks. No one expects a rescue here. No one predicts a hidden boundary where forces suddenly win. At the Big Rip, even the smallest known structures fail. What would you experience if you were somehow alive near this end? First, distant galaxies vanish as distinct objects. Then your own galaxy unravels. The familiar architecture of a solar system, the quiet clockwork of planets around a star, disintegrates. Gravity loses every contest, one scale at a time, until the very molecules in your body can no longer stay intact. You do not freeze in a thin, dark universe. You are disassembled. Compared to heat death, this is not a slow dimming of the cosmic lights. It is a catastrophic disassembly of reality itself, compressed into a finite future. Instead of drifting endlessly beyond the last star, every structure, every memory-bearing pattern is erased in a final, accelerating instant. The mission of the universe does not end with a whisper. It ends with the fabric of space and everything in it torn apart. Now, let's begin to ask an even sharper question. If every bond can be broken by expansion, is there any version of the future where the laws themselves change underneath you, not by pulling you apart, but by rewriting what apart even means? If expansion can rip every bond apart, there is an opposite nightmare. What if the universe slams everything back together? Tonight, we're going to fall into that collapsing universe and watch what it does to you. In the big crunch picture, the mission of space reverses. Right now, distant galaxies are racing away, driven by dark energy. But imagine that dark energy is not a constant or that its strength fades. Gravity would slowly claw back control. Expansion would decelerate, coast, and then stop. Beyond that invisible boundary in time, galaxies that once fled from each other would begin to drift back, as if the entire cosmos had changed its mind. At first, not much changes where you sit. Galaxy clusters tighten, the large-scale web of the cosmic structure shrinks. Over billions of years, the average distance between galaxies falls. What used to be a gentle redshift of light becomes a blue shift. The sky brightens with returning galaxies. The same way the solar wind once carved out a bubble in the local interstellar medium, the whole cosmic web now caves inward, pulled by its own mass. Then the collapse accelerates. The boundary of the observable universe contracts. Regions that were once forever beyond contact rush back into view, but there is no time to visit them. Temperatures rise as gas clouds are compressed. Star formation briefly surges, a last blaze of new suns. But galaxies begin to merge violently, their central black holes spiraling together into titanic monsters. Radiation floods space. The background glow climbs from microwave to infrared to visible to blinding X-rays. Near the end, everything is close to everything else. Distances between galaxy centers could shrink to scales that once separated stars. Matter density climbs toward conditions last seen at the Big Bang. The universe that was once cold and thin becomes hot, thick, and opaque. Every planet, every spacecraft, every archive is dragged into a common inferno. No one expects your hard drives, your neurons, or even your atoms to remain intact in that storm. Some theorists do not stop there. By the end of tonight, you're going to understand why a big crunch tempts scientists to talk about a big bounce. In certain models of quantum gravity, a total collapse cannot reach true zero size. Instead, the universe hits an extreme but finite density, then rebounds. The equations that described a dying cosmos suddenly describe a newborn one, expanding again with fresh initial conditions. But what about you? Could any trace of your information tunnel through the bounce? In principle, information is stubborn. Quantum theory resists true destruction. In practice, the crushing, churning, chaotic mix of extreme gravity and temperature would scramble every pattern beyond recognition. Even if some abstract information is conserved, it would not look like galaxies, planets, or people. It would not look like your memories. Current observations point the other way. An accelerating expansion, not a future crunch. No one predicts a guaranteed big bounce, and absolutely no one anticipates how dark energy might evolve over trillions of years. To know what really happens to you, the universe has one more, even stranger, card to play. So far, every ending has at least given you time. Stars fade, galaxies thin out, black holes evaporate. You could, in principle, watch the curtain fall. Vacuum decay does not offer that mercy. Before we get started, zoom in on a quiet point in space. No planets, no stars, just the quantum fields that fill the universe. To you, the vacuum looks empty. To quantum field theory, it is a seething medium with an energy level, like a ball resting in a valley. The dangerous possibility is that this valley is not the lowest one. Our entire cosmic history could be unfolding in a metastable vacuum, balanced on a ledge that is not the true ground state. In that picture, the universe is living on borrowed energy. Tonight, we're going to stand on that ledge and look down. If there is a deeper valley in the landscape of quantum fields, the vacuum can change its mind. Not gradually, not politely. Through quantum tunneling, a tiny region could suddenly slip into the lower energy state, creating a bubble of what physicists call true vacuum. Now, let's begin to follow that bubble. The instant it appears, it feels an enormous energy difference between itself and the old vacuum. The result is expansion at nearly the speed of light, a runaway front racing through space. There is no shockwave in the usual sense, no fireball, no glowing walls sweeping across the solar system that you might see coming. From your perspective, one moment the familiar laws of physics hold. In the next, they do not. Inside that bubble, everything is rewritten. Particle masses could change, the strengths of the forces could shift. The delicate balance that allows atoms to exist might vanish entirely. Hydrogen might not bind, chemistry might be impossible. Even if some new kind of structure could form, it would not be you. The mission profile of reality itself is different. Here is the key horror. There is no warning. Because the bubble wall moves at essentially light speed, no signal can outrun it to tell you it is coming. No spacecraft can steer around it. No one expects a last sunset, a countdown, or a heroic escape. Your body, your brain, the information pattern that encodes your memories and identity, all are either annihilated or rendered meaningless in a single, seamless, unexperienced instant. Some calculations using the measured mass of the Higgs boson hint that our vacuum might indeed be metastable. The predicted lifetime is staggeringly long, far beyond the current age of the universe, far beyond heat-death timescales. By the end of tonight, you're going to understand that unlikely is not the same as impossible, and that the universe's deadliest ending might already be written into its fields. And yet, there is one more question hanging over you. If the universe can erase you this completely, can anything about you survive at all? So, which death do you actually get? Out of all these cosmic endings, which script is the universe most likely to follow for you, your planets, and every atom you've ever touched? Before we get started, rewind the 4 possibilities. Heat death is the slow fade. Expansion keeps accelerating. Galaxies slip beyond the cosmic horizon. Stars burn out. And after about 10 to the 14th years, no new stars form. In the end, you are not ripped or crushed. You are diluted. Every memory, every structure is smeared into an almost perfectly uniform bath of cold radiation and lonely particles. The Big Rip is the opposite mood. Instead of dark energy staying gentle, its pressure grows. Expansion accelerates so violently that galaxy clusters are torn apart, then galaxies, then solar systems, then planets, then you. In the final instance, even atoms are shredded as space itself outruns the forces holding matter together. The Big Crunch flips the sign. Expansion halts, reverses, and the whole observable universe collapses back in. Galaxies hurtle together, background radiation heats up, and the sky brightens into a lethal furnace. In the final approach, densities and temperatures soar. You are not stretched, but crushed into the same fireball that once gave birth to everything. Vacuum decay plays by different rules. No slow arc, no grand symmetry. A quantum fluctuation nucleates a tiny bubble of a lower energy vacuum. It expands at nearly the speed of light, rewriting the laws of physics as it goes. No one expects a warning, because there can't be one. By the time the boundary reaches you, you are already gone. So, which of these does the data favor? Tonight, we're going to listen to what the expansion itself is telling scientists. Measurements of distant supernovae, the cosmic microwave background, and the large-scale structure of space all point to dark energy behaving like a cosmological constant. Its equation of state is extremely close to -1, with no strong evidence it's drifting. That single fact pushes the Big Rip and the Big Crunch out of the spotlight and makes a heat, death-style ending the leading candidate. But vacuum decay is a separate quantum question. Even in a quiet cosmological constant universe, a decay bubble could, in principle, appear at any time, racing outward through the cosmic wind of galaxies. The probability, given current estimates of the Higgs and top quark masses, is so low that the expected lifetime is far beyond 10 to the 100th years, far beyond even black hole evaporation. There are uncertainties. The equation of state of dark energy could be hiding tiny deviations that long missions and future spacecraft surveys will only reveal over billions of light years. Physics, at very high energies, the realm of grand unification and quantum gravity, might change the stability of the vacuum. Proton decay, if it exists, would quietly dissolve matter into radiation long before some of these timelines play out, but experiments have not yet seen a single event. So, based on what is actually discovered so far, the most conservative forecast is stark. Continued expansion, rising entropy, star formation ending, black holes evaporating, and an ever colder, ever emptier universe. By the end of tonight, you're going to understand that this is not a sudden apocalypse, but a mission that drifts beyond every boundary of time you can imagine, unless quantum instability, hiding in the fields beneath space itself, absolutely rewrites the script. And if that's the likely fate of the system you live in, there's one last puzzle. In a universe that forgets almost everything, can information about you really be erased forever? To answer that, the scale has to crash back down from trillions of years to the next few decades, to something uncomfortably close. Your own body. From the universe's perspective, your death is a local rearrangement of matter. Cells stop repairing themselves. Membranes break. Bacteria, fungi, and oxygen go to work. Tissues soften, collapse, and return to the soil and air. What looked like a single continuous you dissolves into a cloud of atoms that were only temporarily on the same mission. Most of those atoms are lightweights: hydrogen, oxygen, nitrogen, carbon. They slip into groundwater, ride rivers, and evaporate. Some join the atmosphere directly as carbon dioxide, water vapor, methane. Within months to years, wind spreads them across continents. Within centuries, circulation patterns can carry them around the entire planet. The boundary of your presence is already far beyond your skin. Now, let's begin tracing just one of them. Pick a single carbon atom from a protein in your hand. After death, microbes liberate it as CO2. It drifts upward, colliding with nitrogen and oxygen, jostled by thermal motion and global wind. A plant's leaf captures it during photosynthesis, locking it into a sugar molecule. That sugar becomes wood, or a grain of wheat, or a blade of grass that a grazing animal eats. So your carbon atom crosses into another body. It might become muscle in a bird, or cellulose in a tree, or part of a human brain cell firing as someone watches a rocket leave Earth for deep space. By the end of tonight, you're going to understand that this is not poetry. It is chemistry playing out on a living planet. Fast forward thousands, then millions of years. Continents shift. Oceans open and close. Some of your carbon is buried in sediments, compressed into limestone, or released again by volcanoes. Some is locked into shells that sink to the seafloor. Some rides dust storms high into the atmosphere and escapes the solar system entirely, nudged by radiation pressure and the slow leak of gas into interplanetary space. On longer timescales, that dust can fall into new molecular clouds. There, under gravity's patient pull, it helps form new stars and planets. No one predicts which future solar system inherits your atoms. No one expects which rocky world will carry a thin film of chemistry that wakes up and calls itself alive. But the physics is clear. In a universe still making stars, your atoms are auditioning for new roles. Tonight, we're going to push that audition further. As long as galaxies shine and gas can cool, fragments of you can be forged into alien mountains, icy oceans, even the nervous systems of creatures that will never know your name. For trillions of years, the universe is generous with new complexity. But that generosity has an expiration date. Star formation slows, then stops. The great recycling engine winds down. Beyond that point, your atoms don't build, they drift. They become part of an ever-thinning cosmic fog, stretched by expansion into almost perfect nothing. And that raises a harder question. When the universe stops making new stories, what happens to the information that says you were ever here at all? When the universe stops making new stories, it doesn't stop moving your pages. Tonight, we're going to watch what happens when the very letters that spelled out your life are scattered so thoroughly that even your atoms forget you were ever here. Before we get started, draw a line between two ideas, matter and identity. The atoms in your body are old. Many were forged in stars that died before the solar system existed. But those atoms are not you by themselves. What makes you is the pattern, the exact arrangement of about 10 to the 28th power particles, the timing of electrical pulses in your brain, the chemistry of cells talking to each other. Change the pattern, change the person. Heat a brain a few hundred degrees, and the atoms mostly stay, but the structure fails. Freeze, crush, or dissolve it, and again the raw material survives while the intricate wiring that carried your memories and hopes collapses. Scientists understand this as information, a low entropy configuration, improbably ordered compared to all the ways those same particles could be shuffled. Now stretch that idea into deep time. As stars age and die, the gentle warmth that keeps complex chemistry running fades. Thermal motion never stops. Atoms vibrate, collide, react. Bonds break and reform. Gravitational tides pull matter into new orbits. The solar system is not a museum, it's a slow, chaotic mixing bowl. Over millions, then billions of years, your former atoms are stirred into oceans, mantle, atmosphere, perhaps ejected by solar wind or scattered when the sun sheds its outer layers. Here's the pattern interrupt. Imagine someone hands you a deck of cards that is secretly arranged to encode every detail of your life. Then they shuffle it not once, not twice, but 10 to the power of 30 times. At that point, the original order is not just hidden. For all practical purposes, it is gone. The cards still exist. The information does not. That's what cosmic time does to you. By the end of tonight, you're going to understand that this isn't just poetic. From an information theory perspective, the configuration that was you is a tiny island in a vast sea of possibilities. As entropy rises, that island is drowned. The specific correlations between this atom and that neuron, between this protein and that memory trace, are diluted into the overwhelmingly larger space of random arrangements. No one predicts a future where, after trillions of years of collisions, decays, and gravitational encounters, those exact relations spontaneously reassemble. No one expects your atoms to line back up in the same solar system, on the same planet, in the same body. The mission profile of the universe points the other way, toward mixing, smoothing, forgetting. Long before the last black hole evaporates, long before the final photons drift into near-perfect uniformity, every practical trace of your personal structure has been erased. The atoms continue their journey through space, but the pattern that once called itself you has crossed a different boundary, from something that could in principle be recovered to something the universe has truly let go. And yet, there is one more question lurking behind that loss. If identity can vanish while matter remains, what does the universe do with the information of everything else it has ever created? So here is the unsettling twist. Matter can be recycled, energy can be redshifted into near nothingness, but there is a growing suspicion among physicists that information itself refuses to die. Tonight, we're going to follow that suspicion all the way to its most uncomfortable conclusion, that on some level, the universe never forgets you. Before we get started, zoom down beneath planets, beneath atoms, into the quantum rules that govern everything. In that world, the evolution of an isolated system is described by a wave function, and that wave function obeys an equation that is time-symmetric. Run it forward, it evolves. Run it backward, it also works. In principle, every quantum state can be perfectly rewound. This is the principle of information conservation in quantum mechanics. If a system is truly isolated, no information about its exact microstate is ever lost. It is only shuffled, entangled, and hidden. That means if the entire observable universe is treated as one gigantic, isolated quantum system, its full wave function carries, in principle, a record of every configuration it has ever passed through. That sounds impossible. It feels wrong, because on human scales, everything screams irreversibility. Ice cubes melt, stars burn out. The solar wind streams past a spacecraft and never comes back. Entropy increases, and processes that were easy to start are impossibly hard to reverse. No one expects a shattered glass to leap off the floor and reassemble in mid-air. The tension is this. The microscopic laws are reversible, but the macroscopic world is not. The reason lies in the sheer number of possible microstates. When a low entropy pattern, like a living brain or a young solar system, evolves, the information that once described its delicate order gets spread out into unimaginably many degrees of freedom. It is still there in the wave function, but now it is encoded in the correlated jitters of photons, the precise directions of particles, the fine-grained quantum phases that no instrument can track. Apply that to you, the exact quantum state that once encoded your brain, your memories, the electrical storms that pass through your neurons, does not blink out when you die. By the end of tonight, you're going to understand that in principle, those patterns are woven into the universe's overall wave function forever. Not as a ghost, not as a copy drifting through space, but as an exquisitely scrambled contribution to the total state of reality. No one predicts that such information could ever be unscrambled by any civilization that looks remotely like ours. The computational power required would dwarf galaxies. The precision needed would exceed what the cosmic background radiation allows. And yet, as a thought experiment, the door is not fully closed. Imagine an intelligence that can control and read the full quantum state of the cosmos, treating the entire universe as a single, programmable system. With perfect knowledge and perfect manipulation, the laws would not forbid it from running the wave function backward or sculpting a region of space so that the pattern corresponding to you reappears. The same atoms or different atoms arranged in the same microscopic configuration, the same neural firing sequences, the same memories of watching this very video. At that point, a final question waits at the boundary between physics and philosophy. If the universe can, in principle, reconstruct you from its never-forgotten information, would the being that opens its eyes be you, or only a perfect echo? In the far future, as the universe races toward heat death, that question will collide with an even harsher reality. What happens to information when space-time itself runs out of room to store it? When space-time runs out of room to store information, the universe points you toward its most extreme filing cabinets, black holes. Tonight, we're going to open one and ask a dangerous question. If a black hole ever swallowed a trace of you, does any meaningful part of you survive? Now let's begin. Classical physics paints a brutal picture. Anything that falls past a black hole's event horizon is gone. The mass stays, the charge stays, the spin stays. But every detail about what actually fell in, every pattern, every configuration, every memory seems erased. The laws that describe gravity and the smooth geometry of space say there is no way back. No way to reconstruct the original. Quantum theory refuses to accept that verdict. In quantum mechanics, information is sacred. The wave function evolves in a way that, in principle, can be reversed. No one expects the universe to casually shred bits of reality. If information could truly vanish, the entire mathematical framework of quantum theory would start to crack. So scientists are trapped between two pillars of physics that disagree about whether the universe is allowed to forget. Out of that tension came one of the strangest ideas in modern science: holography. In certain models of space, like the famous ADS/CFT correspondence, everything happening inside a region, including gravity, particles, even black holes, can be redescribed as information living on a lower dimensional boundary. The volume becomes a projection of a surface. In this view, a black hole is less a bottomless pit and more a cosmic hard drive, with its information encoded not in the interior, but on the event horizons area. To see what that really means, imagine your life as a file on a computer hard drive. Every heartbeat, every thought, every message you ever sent is written as a long sequence of bits on that spinning disk. Now imagine the disk is smashed, melted, ground into dust, and scattered across the room. Technically, the atoms that carried those bits still exist. The magnetic domains are disrupted, not annihilated. In principle, a perfect super-scientist could track every fragment and reconstruct the original file. In practice, that file is gone. Not because the universe violated information conservation, but because the information is now scrambled beyond recovery. The pattern that was you has dissolved into uncorrelated noise. Black hole evaporation may work the same way. As black holes slowly lose mass through Hawking radiation over unimaginable timescales, up to around 10 to the power of 100 years, for the largest ones, the information they swallowed is thought to leak back out, encoded in subtle correlations between outgoing particles. The mission is technically complete. No bit is truly lost. But the result is like reading a shattered hard drive with tweezers, one atom at a time in random order over a trillion ages. Some part of your history, light reflected from your skin, radio waves from your devices, thermal photons from your body, may already be on a one-way journey toward black holes scattered across the cosmos. The solar system's broadcasts, the faint signatures of your existence, drift through space like digital dust. If those traces ever cross an event horizon, the universe will still contain that information, but only as an almost hopelessly scrambled pattern on a shrinking surface and, later, in a thin mist of radiation. By the end of tonight, you're going to understand that this is the generous scenario. It assumes space-time remains kind enough to keep track of every bit. But in the far future, as horizons multiply and dark energy stretches space beyond recognition, an even harsher possibility appears. What if the universe not only scrambles your information, but tears apart the very stage that makes information possible at all? The harsher possibility is this: the universe doesn't just erase your information, it keeps going. It keeps expanding. And in that thin, cold, almost featureless space, something utterly bizarre can still happen. Tonight, we're going to meet one of the strangest ideas in modern cosmology, the Boltzmann brain. Imagine a self-aware brain floating alone in the dark, with a full set of memories, emotions, and expectations, and a past that never actually happened. No body, no planets, no solar system, just a pattern of particles that, for a brief moment, thinks it is you. In a heat-death universe, entropy is maximized, everything is spread out, uniform and quiet. But in statistical physics, uniform never means perfectly smooth. There are always fluctuations, most are tiny, like a few particles clumping together. But given infinite time and a vast enough volume of space, the equations say rare, huge fluctuations are possible. No one predicts a working brain should appear from thermal noise, yet the math does not forbid it. A Boltzmann brain is one of those extreme fluctuations, an ordered configuration of matter that just happens to match the structure of a functioning brain. Neurons, synapses, firing patterns, all aligned in a way that encodes experiences. Watching this video, walking under Earth's sky, feeling the wind in your face, even though in that distant era, Earth, wind, and sky are long gone. Those memories are false. The brain has never orbited a star. It has never seen planets. But from the inside, it cannot tell. Here is the unsettling twist. In an eternally existing heat death, there is effectively unlimited time for these freak events. Normal observers arise once early on from low entropy beginnings, galaxies, stars, chemistry, evolution. Boltzmann brains arise later, from pure chance. Some calculations suggest that if the universe expands forever, the number of random brains could vastly outnumber the number of ordinary, evolution-produced observers. Now, let's begin to ask what that means for you. Suppose, in the deep future, a perfect copy of your brain fluctuates into existence. For a fraction of a second it wakes up. It remembers childhood, friends, this entire mission through cosmic history. It believes it sits on a living planet under a bright sun. Then the fluctuation collapses and the pattern dissolves back into chaos. From the inside, was that experience any less real? By the end of tonight, you're going to understand why many scientists see this as a problem, not a curiosity. If Boltzmann brains dominate, then a randomly chosen observer with memories like yours is overwhelmingly likely to be one of them. That would make the ordered universe around you, its consistent laws, its long history, its coherent cosmic timeline, statistically suspicious. No one expects a theory of the universe to say, your memories are probably fake. Absolutely no one anticipates that the most successful equations of thermal physics and cosmology might point in that direction. So modern cosmological models are tested not just against galaxies and the cosmic microwave background, but against this nightmare scenario. Many proposed endings, like universes that decay, recollapse, or rip apart, avoid Boltzmann brain domination by ending the show before random observers can take over. In doing so, they force a deeper confrontation with identity and probability. Are you defined by a continuous history through time or only by the instantaneous pattern of your brain right now? Before we get started on the final fates that sidestep this paradox, there is one more boundary to cross. What if the universe doesn't simply fade, but changes its rules mid-game, rewriting reality everywhere at once? Imagine the rules of physics staying the same, the universe just coasting toward darkness, and you refusing to go quietly. Tonight, we're going to follow a civilization that sees the last star dimming and treats it not as an ending, but as a new kind of mission. Picture minds spread across thousands of galaxies long after the solar system is gone. Every bright, young star has already burned out. The sky is a graveyard of white dwarfs, neutron stars, and black holes. The cosmic background has cooled to near absolute zero. In this thin, cold space, scientists of that age face a brutal accounting. There is only so much free energy left, and the clock is running. No one expects them to just sit and watch the lights go out. They build Dyson spheres and Dyson swarms around every remaining star, capturing nearly all of the outgoing power. They throw planets and brown dwarfs into controlled orbits around black holes, farming them, using the extreme gravity to drive turbines of accretion and extract energy from spinning horizons. Reality itself becomes an engineered power plant, tuned to squeeze every usable joule from the fading cosmic wind. But capturing energy is only half the problem. The other half is how to spend it. By the end of tonight, you're going to understand why the real game is information, computation, thought. These civilizations design computers that run at temperatures a whisper above the background, because cooler operation means less wasted energy. Every bit flip is precious, every memory write is a sacrifice. So they adopt heat-death survival strategies. Minds slow themselves so that 1,000,000 years of objective time feels like a second of subjective experience. They hibernate for eons between rare energy events, waking only when a black hole feeds or a captured star flares. Consciousness is encoded into ultra-stable, ultra-low-power substrates, perhaps in matter barely bound together, perhaps in patterns of radiation drifting through intergalactic space. Now, let's begin to pull in the hard limits. Physics does not negotiate. The Bekenstein bound says there is a maximum amount of information that can be stored in a finite region with finite energy. Landauer's principle says every irreversible operation, every erased bit, must generate heat and consume energy. No one predicts a clever hack that gets around these. Absolutely no one anticipates a loophole that lets infinite thinking happen on finite fuel. As the universe expands, usable energy thins out. Even perfect engineering cannot change the trend. Entropy rises, gradients flatten, boundaries blur. Computation slows, then stutters, then stops. The question is unavoidable. Does any form of life or mind, no matter how advanced, have to accept a final thought? Or is there one last move left on the board, hiding not in engineering, but in the deep structure of space-time itself? If there is one last move, it may not be made with flesh at all. It might be made with code. Tonight, we're going to follow you into a universe where your body has failed, your star has died, but something that calls itself you is still running on a machine under a black sky. Before we get started, picture the basic idea. Mind uploading. Instead of neurons firing in a warm, wet brain, a detailed map of your synapses and their strengths is transferred to a digital substrate. The pattern of activity that is you is now an arrangement of bits in some advanced spacecraft computer, humming in deep space, far beyond the planets of the original solar system. In principle, if the pattern and its dynamics are preserved, the experience continues. Thoughts, memories, preferences, the feeling of being inside a world. The mission changes from keeping a fragile body alive to preserving information and running computation. And here, expectation collides with reality. Biological brains leak heat, need constant chemical maintenance, and waste energy. A perfected upload could use cooler temperatures, reversible logic, and error-correcting codes to do the same thinking with far fewer joules. That matters in a universe where energy is running out. As stars fade and the cosmic background cools, scientists imagine civilizations migrating to colder and colder regions, building computers that sip power from black hole accretion, white dwarf embers, or the faint glow of decaying particles. Designed for a brief biological lifespan, minds could now be recompiled as software, tuned to run on picowatts, surviving long after planets and normal stars are gone. But there is another trick. If power is scarce, the simulation does not have to run in real time. A civilization could slow its clock rate as the available energy per second drops. 1 year of external cosmic time might correspond to 1 second of subjective time, then 1 century, then 1,000,000 years. From the inside, consciousness flows smoothly. From the outside, the universe races ahead while the digital minds experience a stretched, almost frozen eternity. By the end of tonight, you're going to understand why even this strategy has a boundary. Physics ties every bit flip to an energy cost. Landauer's limit says erasing 1 bit of information in a computer, no matter how advanced, must dissipate at least a tiny amount of heat proportional to the background temperature. As the universe slides toward heat death, that background temperature drops, so each operation can, in theory, cost less energy. But the total usable energy within the horizon is finite. No one predicts an escape from that arithmetic. Integrate over all future time and you get a maximum number of possible operations. Run fast and bright now, or slow and dim across unimaginable aeons. The sum is capped. Eventually, the last bit flip happens. The last memory is written. The last simulated sunrise over a virtual ocean fades into perfect thermal equilibrium. So digital ghosts of you can outlast your biological body by trillions of years, perhaps by factors of 10 to the 40th or more. They can think long after the last real star has gone out, after black holes have evaporated, after normal matter has decayed. But they cannot outthink thermodynamics. Information can be preserved in principle, yet there comes a time when no new computation, no new experience can occur. The mission of consciousness, transferred from neurons to nanocircuits to cosmic-scale computers, still ends at the same wall: entropy. Or does it? Because there is one more loophole that absolutely no one anticipates on first hearing it, hidden in the dark energy that drives the expansion of space itself. So, if the mission of consciousness hits a wall in this universe, can it simply leave? Tonight, we're going to step right up to the edge of known physics and ask whether the only way to survive cosmic death is to abandon the entire cosmic stage. Now, let's begin. One idea that keeps appearing in serious papers and late-night conversations is the baby universe. Advanced scientists, facing the slow freeze of heat death, might try a different kind of mission, not launching a spacecraft to another planet, but igniting an entirely new region of space with its own laws, its own initial conditions, and a fresh, low entropy beginning. In principle, if the physical constants could be nudged, gravity a bit weaker, dark energy a bit tamer, that new universe might be more hospitable to life and long-term information processing than this one. No one expects that to be easy. The most popular playground for this idea lives near one of the most extreme boundaries in the system: black holes. Some theories of quantum gravity suggest that when a massive star collapses, the singularity might bounce, budding off a new expanding universe on the other side of the event horizon. From our side, it is just a black hole. From the inside, it could look like a Big Bang. In that picture, black holes are not just cosmic trash compactors, they are seeds. The wind of gravity funnels information in, and a new cosmos blooms beyond our view. That raises a wild possibility. Could an advanced civilization in the deep future engineer a black hole in just the right way, that its internal baby universe carries some imprint of them, codes in fundamental constants, patterns in initial quantum fluctuations, a kind of cosmic graffiti saying "we were here," written into the next universe's sky? Then comes the pattern interrupt. What if escape does not require black holes at all? Some proposals imagine manipulating the vacuum itself. In quantum field theory, what looks like empty space can exist in different energy states. If our current vacuum is not the true minimum, then under extreme conditions it might be possible to tunnel to a lower energy state, nucleating a bubble that expands at near light speed. From inside, that bubble would be a new universe, with fresh resources and perhaps completely different particles. But here the contrast between dream and reality is brutal. There is no working theory of quantum gravity. There is no experiment showing that baby universes form, no evidence that vacuum tunneling can be steered, no indication that anything crossing such a boundary would remain intact, let alone conscious. By the end of tonight, you're going to understand that, from the standpoint of current physics, these are not plans, they are thought experiments. And even if some future civilization could light the fuse of a new cosmos, a final question hangs over the mission. Would anything recognizably you make that journey, or would this only create a separate reality where new observers arise, never knowing the universe that died to give them birth? To answer that question, you need a calendar, not of days or years, but of eras. Tonight, we're going to walk through the entire future of the cosmos as a schedule for your disappearance. Now, let's begin. On human timescales, your first deadline is short. Within a century or so, your body returns to the planet that built it. Bones dissolve. Teeth fracture. Even in a sealed vault, chemical reactions and geological motion grind you down. Within about 1 million years, ordinary erosion and plate tectonics can bury and recycle almost every trace of your physical remains into Earth's crust. Zoom out to 10 million, 100 million years. Continents drift, cities crumble. The solar system changes slowly under the sun's wind and radiation. By around 1 billion years from now, the bright, stable sun that fed your entire lineage will have swollen and heated, likely sterilizing Earth's surface. Any books, drives, or digital archives containing your name left unprotected on this planet are ash, plasma, or molten silicate. The mission of preserving you locally has already failed. By the end of tonight, you're going to understand how fast that erasure accelerates. Around 10 trillion to 100 trillion years from now, star formation across the observable universe shuts down. The last red dwarf stars flicker and fade. Planetary systems freeze drift and are torn apart by close encounters and gravitational tides. If some spacecraft or vault carrying your data survives that long, it now orbits a dark, mostly dead galaxy, bombarded by cosmic rays and micrometeoroids until its structure is shredded. Push forward to around 10 to the power of 34 years, the time scale some physicists assign to proton decay, if it exists. At that boundary, every atomic nucleus that once helped build your body, your devices, your monuments, quietly falls apart into a bath of lighter particles and radiation. The atoms that were you are no longer even atoms. Far beyond that, up to roughly 10 to the power of 100 years, black holes dominate. They swallow stars, planets, and the wreckage of civilizations. Some of the matter and information that ever interacted with you may be locked behind their horizons, but hawking radiation is patient. Over unimaginable spans, even supermassive black holes evaporate, releasing their contents as an almost featureless drizzle of photons and particles into space. Meanwhile, the universe expands. Photons that once bounced off your face, your home, your world, stretch with the growing cosmos. Their wavelengths lengthen, their energy drops. Eventually, those signals are redshifted so far into the microwave and radio background that they are indistinguishable from noise. The record is not just hard to read, it is physically scrambled. In the final heat death, there are no stars, no active black holes, no gradients to power memory or mission, only a thin, cold haze of particles and radiation spread almost uniformly. Every configuration that once encoded you has been mixed into the general entropy of the universe. A trace remains only in the most abstract sense. The total disorder is slightly higher because you once existed. The cosmos keeps going. But for all practical purposes, you are gone. And yet, there is one last, more radical possibility the universe may still have in reserve. That one last possibility is disturbing because it forces a final question. When the universe ends, does any version of you survive at all? Now, let's begin. To answer that, you have to peel yourself apart into layers. There is the biological organism, a particular arrangement of cells, chemistry, and brain tissue. There is the psychological you, memories, personality, the continuous flow of experience. There is the social and cultural you, the roles you play, the stories others tell, the influence that ripples through a civilization. Then there is the digital you, data on drives, archives in the cloud, signals from servers and spacecraft. And beneath all of that, there is the bare physical information, the exact microstate of particles and quantum fields that once encoded a human life in this corner of space. By the end of tonight, you're going to understand how each of those layers fares against the cosmic timeline. On human scales, the biological and psychological you are fragile. A few minutes without oxygen, a few decades of aging, a solar flare, an impact, a random mutation. Long before stars fade or the solar system changes, the organism and the stream of consciousness end. No one expects that version of you to see the wider mission of the cosmos play out. The social and digital layers stretch farther. Your name in a language, your work in an archive, perhaps a recording on a future Voyager-like spacecraft, still crossing the boundary of the heliosphere as the solar wind weakens. But compare those to the ages to come. Civilizations collapse. Planets are sterilized or swallowed. Hard drives demagnetize. Atoms diffuse or decay. In a heat-death universe, even the most redundant storage is washed out by trillions of degrees of expansion and entropy. In a big rip, the very bonds between particles are torn. In vacuum decay, a new region of space with different laws sweeps through at near light speed and erases every structure. In all cases, the social and digital, you are temporary eddies in a much larger wind. That leaves the deepest layer, quantum information. Modern physics strongly hints that information is never truly destroyed. Even black holes over unimaginably long times radiate away their contents in a way that encodes what fell in. So in principle, some encoding of your existence persists, smeared into the universe's final microstate, not as a readable file, not as a reconstructible brain, but as infinitesimal correlations in fields that no observer can access. For most reasonable definitions of personal identity, continuous experience, memory, a pattern that could in practice be rebuilt, that does not count as survival. The pattern that was you is not preserved as a coherent structure. It is scrambled, thermalized, and lost to any possible subject. Yet some philosophers argue that if the information is conserved, then in some alien sense you are not fully gone. The record is still there, everywhere and nowhere. The question is whether that counts as existence or as something far stranger. Because there is one more way to think about you that absolutely no one anticipates on a first pass. Because there is one more way to think about you that absolutely no one anticipates on a first pass. Not as a pattern in particles, not as information in quantum fields, but as a finite window of experience in time. A brief mission launched from a tiny planet in a small solar system, in a universe that will one day go dark. And when you first learn that the universe will eventually erase every trace of that mission, it can feel like the floor drops away. If all stars fade, if even black holes evaporate, if the cosmic background itself thins toward absolute uniformity, then the reaction is understandable. Does any of this matter? Does love matter? If the last photon that remembers it will one day redshift into near nothing? Does trying to understand space and the planets matter if even the word understand disappears from the cosmic vocabulary? Different philosophies answer in different ways. Cosmic nihilism looks at the heat-death timeline at 10 to the power of 14 years without new stars, 10 to the power of 40 years of drifting remnants, 10 to the 100th power years until the last black hole evaporates, and says, on those scales, nothing ultimately matters. No one expects your name to survive that long. By that standard, every victory, every tragedy is swallowed by entropy. Existentialism replies with a sharp turn. Meaning is not discovered out there, waiting in some eternal archive. Meaning is created locally by conscious agents who care. The boundary that counts is not the edge of the observable universe, but the edge of a life. Within that finite span, choices are real, values are real, and responsibility is inescapable. Humanism goes one step further. It argues that value arises from experience itself. A single moment of joy, a single act of courage, a single decision to help another mind has value because it is felt, not because the universe will keep a permanent record. The mission log can burn at the end. What mattered was that the mission flew. Here is the pattern interrupt. The finiteness that seems to crush meaning can also supercharge it. A moment is precious precisely because it will not be repeated across 10 to the power of 100 years. A conversation with a friend is not less meaningful because distant galaxies are receding. It is more meaningful because against that vast, indifferent expansion, two tiny regions of the universe briefly synchronize and understand each other. And on human and planetary timescales, your actions matter enormously. They shape the climate of this world, the trajectories of children not yet born, the health of ecosystems, the future of science and spacecraft and missions that will travel far beyond your lifetime. No one predicts that a choice made in a kitchen or classroom will alter the distant solar wind, but it can alter the culture that sends the next generation to meet it. In a strange way, knowing that the universe will end can be liberating. It cuts through fantasies of cosmic permanence. It says, there is no eternal scoreboard, no hidden tribunal. There is only this finite interval of low entropy, this brief clarity before the fog. Tonight, we're going to live inside that interval. By the end of tonight, you're going to understand that the death of the universe is not a verdict on your life. It is the backdrop. Now, let's begin to ask a different question. Given this ending, what kind of universe do you want to help build while the lights are still on? Given this ending, there is one more twist. There is a way the universe could end for you not in 10 to the power of 100 years, but in the next second. No slow fade, no final star, just an invisible blade falling from nowhere. This is the metastable vacuum. In quantum field theory, the vacuum is not just empty space. It is the lowest energy configuration of the fields that fill the solar system and every galaxy beyond. Or at least, it is supposed to be. If our vacuum is only metastable, then somewhere in that quantum landscape, there is a deeper valley, a true vacuum with slightly lower energy, waiting. Tonight, we're going to stand under that possibility for a moment. In that picture, a tiny region could, in principle, tunnel into the true vacuum. A bubble appears. No one predicts it. No one expects it. The boundary of that bubble then races outward at almost the speed of light, turning everything it touches into a new phase of reality with different constants, different particles, different forces. At that boundary, atoms lose their structure, nuclei fall apart, chemistry ends. There is no warning, because no signal can outrun the front. So why are scientists not panicking on live television? Because when the equations are pushed as far as current data allow, the expected lifetime of a metastable vacuum like ours is not 1 billion years. It is far beyond 10 to the 100th power years. On those scales, the probability that a decay bubble appears in the next billion years or the next trillion is so close to zero that for every practical mission, every planet, every civilization, it might as well not exist. Contrast that with other existential threats. Asteroids cross Earth's orbit on timescales of tens to hundreds of millions of years, and the solar system has the craters to prove it. Gamma-ray bursts can sterilize planets across thousands of light years with a single beam of high-energy radiation. Human-made catastrophes, from nuclear war to uncontrolled climate change to engineered pandemics, operate on timescales of decades to centuries. The difference is not just probability, it is control. Telescopes can map asteroids, spacecraft can deflect them, policies and technologies can reduce human-made risks. But a vacuum decay bubble is pure physics. No one predicts it. No one prevents it. So what should you do with that knowledge? Before we get started on despair, notice the choice. An end that cannot be influenced does not demand daily attention. It suggests a different strategy. Focus on the boundary conditions you can actually change. The survival of biospheres, the trajectory of technology, the quality of conscious lives while the cosmic wind still blows and the stars still burn. Paradoxically, knowing that instant oblivion is on the menu can sharpen the present. Every conversation, every mission launched into space, every sunrise over a small rocky world becomes more vivid because there is no guaranteed later. Now, let's begin to ask a harder question. If all you can truly count on is this finite interval, what do you want the universe to remember you for while it still can remember anything at all? If the universe is going to remember you at all, it has to be through patterns written into space itself. So how do scientists read those patterns and turn them into a verdict on the universe's fate? Tonight, we're going to stand next to them as they hold a thermometer up to the cosmos and ask, how does this all end? The first clue comes from exploding stars. In the late 1990s, teams used distant Type 1a supernovae as standard candles to map how fast galaxies were receding. Expectation, gravity should slow the expansion. Reality, those supernovae were dimmer than predicted, farther away, implying the expansion of the universe is accelerating. No one expects empty space to push galaxies apart faster over time. Yet that's exactly what the data revealed. To cross-check, they turned to the oldest light in existence, the cosmic microwave background. Tiny temperature ripples in this afterglow, mapped in exquisite detail by missions like WMAP and Planck, encode the universe's density, geometry, and expansion rate just 380,000 years after the Big Bang. From these ripples, scientists discovered that ordinary matter, dark matter, and dark energy add up to a cosmos that is very close to spatially flat, with dark energy dominating the energy budget today. Then come the galaxy maps. Massive surveys chart how galaxies and clusters clump together across billions of light years, tracing the invisible scaffolding of dark matter and the tug-of-war between gravity and expansion. The pattern of those clumps and the way it changes with distance pins down how the expansion rate has evolved over time, acting like a time-lapse of the cosmic wind pushing the solar system of galaxies apart. Put together, these three lines of evidence constrain the density and equation of state of dark energy, how its pressure relates to its energy. Current data say it behaves very much like a cosmological constant. That rules out some of the most dramatic, near-term Big Rip models where, in just a few billion years, galaxies, planets, even atoms are shredded. By the end of tonight, you're going to understand that the universe is cruelly patient. But the far future is not decided by cosmology alone. Particle physics experiments from giant underground detectors to high-energy colliders probe whether protons decay, how neutrinos behave, and how quantum fields act at extreme energies. Theorists use these clues to estimate whether protons will eventually dissolve, whether our vacuum is truly stable or just metastable, and how fields might behave on scales far beyond any laboratory, right up to the question of sudden vacuum decay. Crucially, this picture is not fixed. Early 20th century models pointed toward a possible big crunch. The late 1990s swung the pendulum toward endless expansion. Future missions, better detectors, and new theories could refine dark energy, reveal proton decay, or uncover new fields that reshape the forecast. No one predicts the next surprise with certainty, but history says one is coming. What is solid are the broad strokes. Expansion continues, entropy increases, stars burn out, black holes evaporate. Those are grounded in well-tested physics of gravity, thermodynamics, and stellar evolution. The details of the ending are speculative. The direction of travel is not. So, if the universe has already written a long, slow fading into its equations, what happens if one of those equations turns out to be wrong in just the right way? Now, let's begin. Imagine the equations broke in just the right way for one last observer to exist. Not a bustling civilization, not a thriving solar system. A single conscious process, hanging on in a universe that has already done almost all of its dying. Tonight, we're going to put you there. You wake up in space that is not the space you know. There are no bright planets, no Milky Way, no familiar constellations. The sky is almost perfectly black. The only glow is a thin smear of background radiation stretched by trillions of years of expansion into a whisper of microwaves, then radio waves, then something so cold it is barely distinguishable from absolute zero. The average distance to the nearest clump of matter is not light years. It is millions of light years, then billions. The last stars went out long ago. White dwarfs cooled into black, invisible embers. Neutron stars drift in silence. Black holes, once the engines of galaxies, now evaporate with a faint hiss of Hawking radiation. Energy is rare. Every usable particle, every temperature difference, every quantum of radiation is as precious as an ocean to a desert traveler. To think, to compute, to remember at all is a mission against entropy. So, what is this last observer? It might be the remnant of a biological mind, uploaded long before ordinary stars died, now running on ultra-efficient hardware, orbiting a dead remnant. It might be a cloud of self-organizing computation spread across interstellar dust. It might be something no one predicts. A pattern encoded in the quantum states around a slowly shrinking black hole. By the end of tonight, you're going to understand that the exact substrate matters less than the experience. With no new starlight, no new planets, no new signals, the boundary between perception and memory blurs. There are no other minds to talk to. No spacecraft to launch, no scientists to compare notes. The only inputs are the faint crackle of radiation and the slow drift of nearby relics. Consciousness turns inward. It replays old data. It reconstructs lost eras. It simulates entire galaxies, entire histories, entire lives, just to have something to think about. There is a choice. burn energy quickly, live vividly, and vanish in what feels like moments, or hibernate between thoughts, stretching each burst of awareness across millions or trillions of external years. 1 second of subjective time could correspond to the evaporation of a black hole. One decision could outlast the visible traces of the Big Bang. Pattern interrupt. This is not a godlike being surveying creation. It is closer to a castaway on an endless, freezing ocean, rationing the last matches. It may spend epochs watching the final black holes shrink, calculating their radiation, tracing how information leaks back into space. It may devote entire ages to running high-fidelity simulations of the early universe, when the cosmic microwave background was warm and the sky was crowded with young suns. Eventually, even that ends. The last meaningful event might be the final photon emitted as the final black hole evaporates. The last observer watches that photon leave, or perhaps feels its energy as the last usable bit of fuel. Then there is nothing left to power thought. No gradients, no winds in space, just thermal equilibrium. Consciousness fades. The last process goes dark. The universe continues to expand. Quantum fields still fluctuate, but there is no one left to notice. And that raises a deeper question. If a cosmos persists with no observers at all, what does it mean for it to exist? So if a universe can exist without observers, the unsettling follow-up is this. How did it ever produce you in the first place? Tonight, we're going to pull the camera all the way back, from your last thought to the first flash of space and time, and then follow the same laws forward until even your final atom is gone. Before we get started, rewind to the beginning. 13.8 billion years ago, there is no solar system, no planets, no boundary between here and out there. There is only an unimaginably hot, dense plasma, expanding and cooling. In the first minutes, protons and neutrons assemble into the lightest nuclei. Hundreds of thousands of years later, electrons finally latch on. Neutral atoms appear. The universe goes from opaque fog to transparent space. Gravity gets to work. Tiny wrinkles in density grow into vast structures. Gas falls together, heats, ignites. First-generation stars light up the dark, fuse hydrogen into heavier elements and explode, seeding the cosmos with carbon, oxygen, iron. New stars form from that enriched gas. Around some of them, planets condense. On at least one of those worlds, in one ordinary-looking solar system, chemistry crosses a boundary. Molecules begin to copy themselves. Life appears. By the end of tonight, you're going to understand that you are not an exception to cosmic evolution. You are its latest experiment. Your blood's iron was forged in supernovae. The calcium in your bones was cooked in long-dead stars. Your brain is a temporary pattern powered by free energy flowing from a hot sun into a cold sky. Low entropy makes you possible. The same physics also writes the ending. Stars burn through their fuel and die. Star formation slows, then stops, after about 10 to the 14th power years. The bright era of galaxies gives way to a dim archive of white dwarfs, neutron stars, and black holes. In the Degenerate Era, even those embers cool. If protons decay, then on scales of 10 to the 34th power years or more, every remaining atom dissolves into radiation. What used to be your body, your planet, your entire galactic neighborhood becomes a thin bath of particles. Beyond that, only black holes remain, slowly evaporating through Hawking radiation. The largest could take up to 10 to the power of 100 years to disappear. No one expects a dramatic finale. No one predicts a last great signal. They just fade, one by one, until there are no structures left to collapse, no gradients left to exploit. What's left is heat death, a universe still expanding, still governed by quantum fields, but so uniform that no mission, no spacecraft, no thought can ever form. The same equations that once assembled you now erase every trace of you. Information is smeared out, scrambled into near-perfect disorder, and yet, viewed as a whole, this is not a tragedy. It is a complete arc. The universe wakes up briefly through beings like you, becomes aware of its own laws, its own history, its own boundaries in space and time. Then, over unimaginable ages, it slowly falls back asleep. In the next section, the question becomes, what does it mean to live well, knowing how the story ends? So, when you hear that the universe will one day fall back asleep, it can feel like a hard stop, a clean, sharp edge at the end of time. But if Voyager taught anything, it's that what looks like an edge from far away almost never is once you get close. Before we get started on how to live inside that knowledge, step back to a different frontier. Tonight, we're going to use one of the smallest, faintest machines ever launched to think about the largest ending imaginable. 2 spacecraft, each with less memory than a calculator and a transmitter weaker than a refrigerator light, were sent to skim past a few outer planets and then fade into silence. That was the plan. A neat boundary, a 5-year mission. Reality refused to stay inside that line. The original models of the solar system's edge were simple. The sun blows a bubble in space with its solar wind. That bubble ends at a termination shock and a sharp heliopause, somewhere around 90 to 100 astronomical units. A round cavity, a clear wall, and outside, clean geometry drawn on a blackboard. Then Voyager actually went. Voyager 1 crossed the termination shock, not at 75 astronomical units, but at 94. Voyager 2 hit it at a different distance again. The heliopause wasn't a crisp shell. It was ragged, asymmetric, pushed and dented by the interstellar wind as our whole solar system plows through the galaxy. The magnetic field twisted in ways no one predicts. The space beyond was hotter, denser, stranger than scientists expected. The boundary was farther. The shape was wrong. The transition was messy and layered, not a single line, but a region of competing pressures and tangled fields. No one expects that from equations alone. Only when a tiny spacecraft actually crossed the frontier did the real structure reveal itself. Now, let's begin to see the parallel. Cosmology once treated the universe's ending the same way. A simple diagram, a clean choice between big crunch, eternal slowing expansion, or a quiet heat death. Then dark energy appeared in the data, the expansion started accelerating, and the menu of endings changed. Heat death with an ever faster expansion, a catastrophic big rip, a sudden vacuum decay that rewrites physics at nearly light speed. Each one moves the supposed edge of time into a different place. By the end of tonight, you're going to understand that even those scenarios are probably sketches, not final maps. Quantum gravity might change what happens near black holes. Proton decay might or might not erase matter. Vacuum stability might shift with energies no experiment on Earth can reach. The end could be smoother, stranger, or closer than current models allow. Voyager becomes more than hardware here. It is a metaphor for human curiosity, fragile machines flung into the dark, still sending back whispers long after every warranty expires, carrying a golden record that tries to speak for an entire species across millions of years. In the same way, your theories about cosmic death are messages projected forward, attempts to make sense of conditions you will never personally see. Thinking about the universe's death is its own boundary-crossing mission. A mental Voyager flight to the edge of what physics can currently say, and then a little bit beyond, into the realm where equations go quiet and values, choices, and meaning have to take over. The next question is not just what the universe will do as it ends, but what you should do, knowing that Horizon is out there, and what happens if the edge you think you see is, once again, not the real one. So here is the twist. For almost all of that unimaginable future you just glimpsed, the universe is quiet, thin, and dark. Yet you are alive in the brief, noisy exception. Tonight, we're going to zoom in on that anomaly, the tiny, impossible sliver of cosmic time where beings like you can exist and even worry about the end. Before we get started, anchor the scale. The universe is about 13.8 billion years old. In a heat-death picture, meaningful structure fades by around 10 to the 14th years. Black holes can linger to 10 to the 100th years and beyond. That means the bright, structured, star-filled era is a razor-thin scratch near the left edge of an almost endless timeline. No one expects complexity to be the default. The default is equilibrium. Hydrogen and helium spread out. Gravity slowly pulls, stars flicker on, forge heavier elements like carbon, oxygen, iron, and then throw them back into space. Only after several generations of stars have lived and died do planets with rich chemistry even become possible. You exist after that forging, but before the long slide back toward uniformity. Think about how narrow that window is. Too early in the solar system's history, and there are no stable planets, no protective magnetic fields, no long-lived stars to bathe worlds in steady light. Too late, and star formation has shut down, the interstellar medium is thin and cold, and the last red dwarfs are burning out. Your entire species appears in a cosmic sweet spot. Enough metals for rocky planets, enough free energy from stars, enough time for evolution to stumble into nervous systems that can notice all of this. Now, pattern interrupt, shrink the whole lifetime of the universe from Big Bang to final evaporation of the last black hole into a single calendar year. On that scale, humans don't show up in December. Human civilization is not the last day. The entire span of recorded history is less than a fraction of a second before midnight on December 31st. Your individual life? A microscopic flicker inside that fraction. This exact moment, watching this video, it's a vibration inside that flicker, already gone by the time you finish this sentence. But scarcity is not an insult. It is the reason diamonds are valuable and starlight in deep space is beautiful. Your consciousness is a fleeting, extraordinarily rare configuration of matter and energy, held far from equilibrium by a local cascade of solar photons and chemical reactions. Out of all the ways particles in this universe could have been arranged, they are for a while arranged as you. By the end of tonight, you're going to understand that insignificant is the wrong word. You are not a speck lost in an indifferent system. You are what happens when the universe, for a brief, improbable moment, becomes able to look back at itself, ask questions, run missions, launch spacecraft, and imagine futures it will never see. The next step is to ask what that awareness is for. and what you choose to do with a universe that will not last. So take that awareness and push it to an extreme. Imagine the calendar of the cosmos flipped all the way to the last page, the final flicker of usable energy, the universe coasting toward heat death. In that fading sea of near-nothingness, you get one impossible gift, the chance to leave a single message behind. Tonight, we're going to ask what that message would be. Not a whole library, not a data center packed with drives, one pattern, one compressed signal. If you could encode a single message, memory, or structure to survive as long as physics allows, what would you choose? A sentence, a song, a map of the solar system, or just a quiet pulse that says, in the simplest way possible, we were here. Now, let's begin. First, think about the ways such a message could be sent. The obvious answer is physical artifacts, golden records, etched crystals, tungsten plates drifting through space on hardened spacecraft. Those can last millions, maybe billions of years as they wander beyond the planets. But in a universe that runs for 10 to the power of 100 years or more, that is a brief echo, not a final word. So the thought experiment escalates. Some scientists imagine encoding information into digital records buried deep inside dead worlds, frozen vaults under the last surviving dwarf planets, or even into engineered particles. Others speculate about writing with gravity itself using cosmic scale structures as a kind of intergalactic billboard, bending or clustering matter so that its pattern carries a message long after stars and normal chemistry are gone. Then the ideas get even more extreme. Could a civilization modulate gravitational waves, sending ripples across the cosmic background as a kind of universal broadcast? Could it imprint information into the spin states of particles, or into the subtle correlations of quantum fields that survive black hole evaporation? No one expects these schemes to be easy. No one predicts they are anywhere near current engineering. But they reveal the lengths a thinking universe might go to in order to be remembered. By the end of tonight, you're going to understand a hard truth beneath the fantasy. In practice, every specific message is almost certainly doomed. Proton decay, black hole evaporation, and the relentless drift toward maximum entropy wipe out structure, erase records, and smear meaning into uniform radiation. The final microstate does not care what language was spoken, what music was written, what missions were flown, and yet this is exactly why the exercise matters. When forced to pick one thing to send to the end of time, priorities sharpen. Some would choose mathematical truths, hoping that prime numbers or the structure of quantum theory say something timeless about reality. Others would choose art or music, a single symphony or image that distills what it felt like to be conscious in this system. Others would send a record of humanity's story from first fire to last spacecraft. Some would keep it even simpler, a pattern that just encodes we existed and we wondered. So pause and aim that question at yourself. If the universe's final microstate could remember one trace of you, even though no one will ever read it, what would you want that trace to be? An achievement? A relationship? A question? The answer says less about physics and more about what you decide to do with the finite time you actually have before the far future arrives and the universe writes its own ending. So, what do you do with that knowledge that the universe will forget you, that even black holes and atoms have an expiration date? Tonight, we're going to take that cosmic erasure and flip it, not by denying it, but by asking what it makes possible right now. Stories are meaningful because they end. A novel that never finished, a movie that never rolled credits, a mission that never ran out of power would stop feeling like a story and start feeling like static. An infinite, perfectly unchanging universe would be like a book with no last page, no tension, no urgency. In a cosmos where nothing could ever truly change or conclude, you could never really arrive or matter or be lost. By the end of tonight, you're going to understand that a finite, evolving universe is harsher in some ways, but far more hospitable to meaning. Stars ignite and die. Galaxies collide. The solar system itself has a limited run. That finiteness is the same reason a single conversation can feel precious. A single lifetime can feel like a whole era. Awareness of mortality, personal and cosmic, acts like a lens. It sharpens the ordinary. The next time you feel sunlight on your face, you are feeling a brief phase in stellar evolution, powered by nuclear fusion that will not last forever. A sunset is radiative transfer through a thin atmosphere on a cooling planet that will one day be uninhabitable. Laughter with a friend is the coordinated firing of fragile neural tissue in a species that appears for a geological instant and then is gone. Nothing in physics requires those moments to exist. No one predicts that chemistry must generate consciousness, or that this particular planet must orbit this particular star in a quiet arm of a galaxy. Yet here they are. Coffee in a warm room, a message from someone who cares about you, a small act of kindness that slightly rearranges the future. So there are two attitudes available. One says, if everything ends, if heat death or vacuum decay eventually erase every trace, then it was all pointless. The other says, if everything ends, then the sheer unlikeliness of existing at all is astonishing, and gratitude is a rational response. Both are understandable. One drains your limited time, the other empowers it. Think of the universe as a cold, expanding night, and life as a campfire. Almost all of space is dark and near absolute zero. The solar wind thins into the interstellar medium. Galaxies drift apart into isolation. But around this temporary fire of starlight and chemistry, conscious beings gather, share warmth, exchange stories, and then, one by one, step back into the dark. Now, let's begin to see your life as part of a grand, finite performance. The curtain will close on the mission of your body, on your planet, on the galaxies, on the very fabric of the observable universe. You do not control the ending. You do control how you use your time on stage, what questions you ask, what you build, who you help while the lights are still on. And here is the unsettling, exhilarating part. If the universe is a limited show, then this exact scene, this century, this solar system, this fragile web of minds, is a once-only act. The question is not whether the theatre burns down in 10 to the power of 100 years. The question is what you do before the next act of the cosmos begins, and the universe reveals that its ending might be stranger than heat death alone. So, from that once-only act, pull back and look at the whole script you now hold in your head. Tonight, we're going to stitch together everything you've just crossed, from this warm, bright century to a universe so old that even black holes have faded into a thin, featureless glow. First, the headline, Physics. The universe is about 13.8 billion years old. Space is expanding, and that expansion is accelerating. Dark energy is driving the galaxies apart, pushing the cosmic web beyond every local boundary. In that picture, entropy keeps rising, energy spreads out, and heat death looms. a final state where no usable gradients remain and nothing interesting can happen. But heat death is not the only script scientists have written. Turn one dial on dark energy and you get the big rip, where the expansion grows so violent that galaxy clusters, galaxies, solar systems, planets, and finally atoms are torn apart. Turn another and you get a big crunch where expansion reverses and everything collapses back into an ultra-hot, ultra-dense finale. Add quantum fields and you unlock vacuum decay, a bubble of lower energy space racing outward at nearly light speed, rewriting the laws of physics and erasing every structure it touches instantly, everywhere, with no warning. Now, let's begin to place you along that arc. From today through about 10 to the 14th power years, you live in the stelliferous era, the age of stars. New suns ignite, solar systems form, planets circle in the dark. Then star formation stops, white dwarfs cool, red embers fade. By around 10 to the power of 34 years, if protons decay, every familiar atom in your former body has dissolved into radiation. Push farther. By 10 to the 40 to 10, to the 50 years, the Degenerate Era gives way to the black hole era. Almost everything left of galaxies has fallen into black holes. By about 10 to the power of 100 years, even the largest of those evaporate via Hawking radiation, returning their mass to an almost uniform sea of low-energy particles. Beyond that, the universe coasts toward final equilibrium. No stars, no planets, no meaningful clumps at all. Through this entire mission you have been the thread. Your body died. Your solar system dissolved, your atoms were scattered, captured, swallowed, re-emitted. Then even the information about how those atoms were once arranged into you was stretched, scrambled, and diluted into the background. In principle, quantum mechanics hints that information is conserved. In practice, it becomes unreachable. Buried in correlations no spacecraft or civilization could ever reconstruct. That is one of the deepest insights you now own. Survival strategies have limits. Dyson spheres, galaxy-spanning computers, black hole data vaults, all of them run into the same rising entropy, the same dwindling free energy, the same distinction between physical persistence and personal identity. Something can endure as particles in space while everything that made it a person has long since vanished. By the end of tonight, you're going to understand something rare. You can now tell a coherent story, from this second in this solar system all the way to 10 to the power of 100 years and beyond, about what will happen to you when the universe finally dies according to the best physics discovered so far. The question now is not whether the ending is coming. The question is how that knowledge bends what you do with the tiny, bright interval you actually get. So here is the uncomfortable, liberating twist. Your entire existence is a microscopic flicker in a universe that will run for 10 to the power of 100 years and beyond. And that flicker is still yours. No one expects a handful of decades on a small planet around an ordinary star to matter next to black holes and heat death. But it does matter, because it is the only slice of eternity you will ever directly feel from the inside. Think of your life as a tiny, bright window cut into the universe's timeline. Behind you, 13.8 billion years of stars igniting, galaxies colliding, planets cooling. Ahead, protons possibly decaying, the solar system dissolving, the last black hole evaporating into a thin hiss of radiation. Your window is maybe 80 trips of this planet around the sun. Within that narrow interval, you have something the rest of cosmic history does not obviously have: awareness, choice, the ability to aim your attention. Tonight, we're going to use that cosmic scale as a lens, not a verdict. If the universe is heading toward a heat death where every temperature equalizes, what do you do with a few warm, out-of-equilibrium decades? By the end of tonight, you're going to understand that the question is less, how long will this matter, and more, to whom does it matter while it exists? That shift changes how time feels. Minutes stop being obstacles to kill and start looking like non-refundable pieces of your slice. Look at relationships through this frame. Stars will burn out, galaxies will drift beyond each other's reach, the solar wind will fade, and the cosmic microwave background will cool toward absolute zero. The people you care about are brief, fragile concentrations of consciousness in that vast, cooling sea. Investing in them, listening to them, building memories that only a few brains will ever store may not echo across 10 to the power of 100 years, but it transforms the only region of space-time you can actually influence. The same is true for curiosity and creativity. The universe will not remember if you binge collected possessions, but every time you learn a piece of how space works, every time you contribute a line of code, a painting, a poem, a small experiment, you are increasing the local density of understanding. Scientists mapping dark energy, a teacher explaining gravity to a child, an artist painting the night sky. These are practical ways of pushing back, for a moment, against the flattening pull of entropy. So, what changes when you know that no choice will literally last forever? It becomes honest to aim for impact on other conscious beings rather than on eternity. Help someone suffer less. Help someone understand more. That is a form of immortality measured not in years, but in minds changed and lives nudged onto different trajectories. Before we get started with the final, strangest implications of all this, share something. How does knowing the universe's fate make you feel about your own mission here? In the comments, describe one thing you might do differently with your slice of time now that you have seen where the timeline ultimately leads. Because if you're still here, listening to how the universe ends and what that means for a single human lifetime, that already says something about who you are. You are not just a passive passenger in a solar system drifting through the space. You are part of a tiny group of minds that insists on looking up, on asking how stars are born, how time flows, and how everything, planets, black holes, memories, might finally disappear. No one expects that impulse. No one predicts a species that stares down its own cosmic obituary for insight. So, before we get started with the last and strangest scenarios, heat death, big rip, vacuum decay, take a second to leave a like if this journey has shifted how you see your place in the timeline. That single click sounds trivial. It is not. On this platform, those tiny signals are the solar wind that pushes a mission like this farther out, beyond its original boundary. When you like, when you comment, when you subscribe, you are not just helping a channel. You are changing what kinds of questions the algorithm thinks deserve to exist. You are telling the invisible systems that control attention that there is value in 10 to the 100-year timelines, in hawking radiation, in wondering whether information about you can survive the evaporation of the last black hole. So if you want more deep dives into how this all works, into whether any form of life or simulation could outlast heat death, into how vacuum stability might decide whether the universe ends slowly or with one catastrophic phase transition, into the information paradox and whether we live in something like a holographic universe, hit subscribe. By the end of tonight, you're going to understand just how fragile everything is and just how powerful it is to understand that fragility together. Think of it as extending the mission. Voyager was designed for 5 years. It has lasted for decades because scientists kept listening, kept funding, kept sending commands through the dark. Engagement does the same thing here. It lets future episodes go deeper, bring in more research, more simulations, more interviews with the people who spend their lives trying to calculate the end of time. Tonight, we're going to follow the universe past every familiar landmark, past the last star, past the last galaxy, past the last black hole. The question is not only what happens to space, but what happens to meaning when entropy wins. Thank you for being part of this, not just for watching, but for being one of the rare humans who looks at an ending this absolute and still asks, calmly and bravely, what should a finite life stand for in a universe that does not last? Now, let's begin. So, return to where this began. A human under a night sky, looking up. At first, those points of light were just distant suns in an expanding sea of space. Now, you know their origin in a hot, bright beginning, and you know their destination in a cold, thin ending where even atoms may not endure. Tonight, we're going to let that knowledge settle, not as despair, but as perspective. Because the same physics that sketches the death of every star also reveals something else. Right now, you are living in one of the brief, blazing chapters when the universe is outrageously alive. Galaxies collide, new stars ignite, planets still orbit in the temperate zones where chemistry can wake up and ask questions. Picture the last star. Not in 1,000 years or 1,000,000, but in something like 10 to the 14th power years, long after every familiar constellation has dissolved, a lone red ember in a sky that has forgotten the word blue. It flickers, burns its final hydrogen, and fades. After that, only black dwarfs, neutron stars, and black holes remain, drifting through a darkened cosmic ocean. Then even those anchors go. Black holes, those great sinks of the solar system and beyond, slowly leak away through Hawking radiation. The largest might take up to 10 to the power of 100 years to evaporate, exhaling their hoarded information as a thin, cold wind of particles into almost perfect emptiness. No one predicts a dramatic finale. No one expects a cosmic curtain call, just a universe cooling toward heat death, its temperature sliding closer and closer to absolute zero. By the end of tonight, you're going to understand something subtle. Knowing this does not make your life smaller. It makes your moment rarer. From a tiny patch of rock around an ordinary star in an ordinary galaxy, a species of primates built spacecraft, mapped the solar wind, traced the boundary of the heliosphere, and then dared to calculate the fate of everything. Scientists took a few centuries of data and extended their vision across 10 to the power of 100 years and beyond. That is not nothing. That is astonishing. The original plan for existence could have been simple: stars form, stars die, no one notices. Absolutely no one anticipates that in at least one corner of this vast system, matter will wake up, name itself, and worry about entropy. Yet here you are, a brief configuration of atoms that can imagine the end of atoms. So here is the quiet reassurance. The universe will end. That has no power to erase the reality of this second, the conversation being had, the breath being taken, the decision to be a little kinder, a little braver, under a sky that will not always be there. If you can, step outside after this, look up. Those stars are temporary, so are you. But for a short span in a long, dark universe, you and the cosmos overlap. You get to be here, conscious, curious, tracing the story from the first light to the last ember. And the real cliffhanger is not how the universe ends, but what you choose to do with the part of its story that has been handed to you right now, before the stars go out